I would like to invite the next our speaker, is Alberto Sicora. The title, Brazilian Disc, Test Circular Force and Seismic Methods.
Well, okay. Thank you, Mr. Chairman. I would like, first of all, to thank the other co-authors of this work. So, Professor Torabi and Dr. Edison from the University of Tehran and Professor Cornetti from Politecnico di Torino. Well, an infinite plate containing a circular roll and subjected to a generic biaxial loading probably represents one of the oldest geometry investigated in fracture mechanics. Let us just think of the stress field solution obtained by Kirsch more than 1 century ago, and on the well-known stress concentration factor concept. Nevertheless, basically, the problem is still object of investigation due to some relevant discrepancy detected between experimental data and theoretical predictions by brittle fracture criteria based on a critical distance. These criteria basically evaluate the stress and or the energy at the finest distance from the notch and compare them with some material properties. And the critical distance generally is a function only of LCH, which is characteristic length, also known as the Irwin's length, through the fracture toughness, K1C, and the tensile strength in MU. So in other words, basically just two material properties are involved, the material fracture toughness and the tensile strength. And among these criteria, I want to focus the attention on the coupled approach which was proposed by our research group. As you can see, the criterion is based on a system of two inequalities. The former, you can see on the right there, the former is a stress condition according to which the average stress field must be greater than the tensile strength, and the second one is an energy balance according to which the energy available over on a graph of increment graph of length delta must be greater than the fracture energy, and the energy balance can be written in terms of the stress intensity factor function and the fracture toughness by means of Irwin's relationship. Of course, I mean, if sigma y, if the stress field is a monotonically decreasing function, and basically if K1 is a monotonically increasing function, the stress condition provides an upper bound for what concerns delta, and the energy balance provides a lower bound for what concerns delta. So for positive geometries at failure, the system becomes a system of two equations in two unknowns. One is the failure stress, which they embed in the stress field and the stress intensity factor functions, and the other one is the critical crack advance, which is a structural parameter. So it does not depend only on the material properties, but also on the geometries, on the geometrical basically factors, on some geometrical factors. And the approach, which is similar to that proposed by Leguillon in 2002, which was based on a pointwise stress condition, to be honest, allows to overcome some drawbacks related to approach based just on stress or energy conditions. Now, this is what I was telling you in the introduction. So these were some tensile tests which were carried out by some scientists in 2006. So there were samples containing a circular roll. The material was PMMA, and you can see here the comparison between experimental data and theoretical predictions. They consider also fine fracture mechanics, they consider also the cohesion zone models, and you can see that the agreement is rather poor. So basically there was a huge scientific discussion on these results, because for instance the authors proposed, they stated that a criterion involving just two material properties was not sufficient, was not good to catch these results. So they proposed a new criterion involving a third material property, which they name fracture toughness, plane strain fracture toughness. Some other scientists proposed basically to fit the material properties, so to consider a criterion with just two material properties, but fitting them in a proper way. And we decided basically to perform new experimental tests as a starting point, and you can see here we consider two materials, GPPS and PMMA. You can see here a picture of the specimen, and also here the experimental data and theoretical predictions by fine fracture mechanics. Here you can see you go towards 1/3, so of the stress concentration factor by Kirsch. So basically, probably our conclusion was that the authors in the previous work, probably they had some problems with experiments. To be honest, good results for composite materials with a circular hole were also obtained by Kamani et al. And Furtado et al. In some recent works. So this is basically the key, the starting point of our analysis, because after these results, we decided to go on with experiments, and our colleagues in Tehran carried out some Brazilian disc tests on samples containing a circular hole. You can see here the geometry. Basically, R is the diameter, 2R is the diameter of the hole, while 2R0 is the diameter of the disc, T is the thickness. We consider again two materials, PMMA and GPPS. You can see, you can read it here, basically the dimension of the samples and all size was small enough in order to reproduce an infinite geometry, so in order to neglect basically boundary effect. And the thickness, which was different from PMMA to GPPS, was anyway large enough to get plane strain conditions. So you can see here some pictures on the samples with different hole sizes before basically failure. You can see here also the material properties which were measured, and interesting, the same value of LCH of the increased length, which was nearly 0.5 millimeter, was estimated for both materials, and this was the loading rate. And finally, I will show you some stress strain curve, which our colleagues sent us. Well, the behavior is similar for both materials, and as you can see, it's linear if the hole size is not very small, but for the smallest hole, you can see here, QR equal to 0.5 millimeter, the behavior becomes nonlinear. And this was observed both for PMMA and GPPS. Now, in order to now apply fine fracture mechanics, so in order to get theoretical predictions, we started to observe that if we remove the hole here in the center, that's the stress field. You can see it on the right. The stress field situation in the center of the disc, where sigma is nominal stress, basically, and this relationship is rather well known. So, the situation is equivalent to this one. So we have an infinite plate, a circular hole with radius r, and the infinite plate is subjected to biaxial loading, sigma along with the y-axis and lambda sigma along basically the x-axis. Lambda is a loading parameter, and of course in our case, Brazilian disc test, lambda is equal to -3. So here I have rewritten the fine fracture mechanics criterion. There is a stress condition, sigma bar is the average stress, K bar is the average stress intensity factor, and here I have rewritten them by means of dimensionless quantities. So in order to apply it, we need two functions, the stress field and the stress intensity factor functions. So no problems for the stress fields, because we are in the framework of linear elasticity. We can exploit the principle of effect superposition, and so we can take the solution by Kirsch, which yields to this value of the stress concentration factor 3 minus lambda, so 6 in our case. And no problems also for what concerns the stress intensity factor function, since it can be found tabulated in some handbooks. Now, what is interesting is that this function here, K1 of A tilde, for lambda comprised between -2.6 and 1, this leads to a positive geometry. But if lambda is less than -2.6, the geometry is locally negative and globally positive. So what do I mean? Here I decided to plot the results for lambda is equal to -6 in order basically to stress the behavior, but of course it's similar for lambda is equal to -3. So here you can see K1, the stress intensity factor function, and K bar, the average stress intensity factor. And you can see here that there are two values, delta star and delta double star, according to which K bar attains basically the same value. Now, what is the situation? The situation is that if the crack advance fall in these regions, basically, if the output of the FFM system falls in this region, there are no problems, basically. I can implement this true condition and I can get the solution both in terms of the crack advance and in terms of the failure stress. But if I'm in the middle region, so if the output of the coupled system falls in the middle region, I cannot accept the solution. Why? Because of course, basically, if I consider delta star, this will lead to a lower failure load. So how can I implement the coupled criterion in this case? Well, I can basically, so if I'm in this region, I have to go back, I have to impose delta star in the energy balance, and of course, in this case, going back, since the stress condition provides an upper bound, if I go back, the stress condition is trivially fulfilled. So, in this case, the coupled system is reduced basically to this energy condition only by imposing the crack advance. This concept dates back to a work by Matic in 2009 and was recently implemented by some German scientists. And what I've just tried to explain to you in terms of the crack advance can be thought also in terms of hole radius. I mean, if I consider a very small hole size, so that's the stress curve, and the stress condition is satisfied for all the points above basically the stress curve. And the same applies for what concerns the energy curve. So, if I choose basically a very small hole size, the minimum, in this case, is provided by the intersection point, and the critical crack advance coincides basically with this point. If I increase basically the hole size in a proper way, of course, that's the situation. So in this case, the minimum, the point according to which the dimensionless failure stress is minimum, is no more the intersection point, as you can see, but it's the minimum of the energy curve. And this is what I tried to explain you 2 slides ago as concerns the other diagram. And finally, if I decide to increase again the hole size in a proper way, I go back to the former situation, so again, the solution is provided by the intersection point between the 2 curves. So, in other words, that's the failure stress as a function of the hole radius. There exists 2 basically values, R double star and R star, according to which, if the hole radius fall in this region, I must implement basically the coupled criterion by means of the energy balance by imposing the crack advance as I showed you before. On the other hand, if I'm here or if I'm there, basically for the extreme values, I can apply the coupled systems. And these were the results for lambda is equal to -6. Of course, as I told you before, the behavior is, let me say, singular for lambda less than -2.6. And that's the behavior for different values of lambda. You can see there are some values for R star and some values for R double star. And as lambda tends to infinite, R double star here tends to 0, and R star tends to 1.44, which of course, I know what does it mean because I made some basically estimations, and that's the asymptotic values for compression. So if I consider an infinite place under compression, I get exactly this value, 1.44. But now, of course, we go back to Brazilian disk test, the Brazilian disk test on samples containing a circular hole. So lambda is equal to -3, and both for PPA, MMA, and GPPS, the characteristic lengths were 0.5 millimeters. So I'm more or less here. And now, for the smallest hole, basically I'm inside this region. So in order to apply Faraday-Fachek mechanics, basically I must implement just the energy condition. On the other hand, for all the other basically hole size, I'm above the upper curve, so I can implement basically the coupled system without any problems. And so, finally, let us say for lambda is equal to -3, what is the comparison between theoretical prediction and experimental data? You can see here the failure stress as a function of the hole radius. You can see both the GPPS and PMMA. Well, as you can see, theoretical predictions tends always to overestimate the experimental data. But the accuracy is quite good. I mean, is rather good for all the cases, except for the very small hole size, where it's above 20%, which is, of course, it cannot be accepted. But this concept, according to us, at least cannot be imputable to the concept of instability, stability, which I showed you before. But according to us, the discrepancy is related to some linear phenomena related to the high failure load and the particularly compressive loading condition. If you remember the stress strain curve for the smallest hole sizes was rather non-linear, and the same basically curve was not the same behavior was not observed when testing tensile basically samples. So property is related to the geometry, to the compressive loading conditions. So to conclude, basically, we have investigated side effects 1/6, if you remember. In Brazilian samples containing a circular hole, both from an experimental point of view by considering two materials, and from a theoretical point of view by implementing fine fracture mechanics. The agreement is, in terms of failure stress, is generally acceptable, but for very small hole size. But what is probably most interesting, according to us, is that for very small hole sizes, the geometry is locally negative and globally positive. So as a future work, our idea is to carry out experiments by reducing either the ratio R over LCH, and since machining very smaller holes, it's very, very difficult. Probably it's better to increase LCH, so it means to consider less brittle materials, or the loading parameter lambda, in order to be in the middle region. And in the middle region, what is interesting is that the subsequent propagation will be not unstable, but will be stable. So we can basically make some further consideration once we have carried out these kind of experiments. So thanks for your attention.